Okay, welcome. Here's a video giving an example problem on traveling waves. And let's see here. We have an infrared light source signal in an optical fiber with a frequency of 193 terahertz. Okay, let's calculate the period in the units of seconds. Let's convert that period into nanoseconds. It's supposed to say nanoseconds here. Let's assume that the light beam is propagating at 2 times 10 to the 8th meters per second and calculate the wavelength. We'll express that in meters, and then we're going to change the wavelength in the nanometers, and then finally into micrometers. Okay? So let's first of all write down what we're given. We're given a frequency F is 193 terahertz. And you know what I'm going to do? I'm going to convert that into 193 times 10 to the 12th hertz. Okay? Now I'm going to plug in to find the period. The period, T, is 1 over F. And so 1 over 193 times 10 to the 12th, I can do that on my calculator. 193 times 10 to the 12th. And now I'm going to raise that to the minus 1. And I get 5.18 times 10 to the minus 15th. 5.18 times 10 to the minus 15th. And this is going to be seconds. Okay? Now they wanted us to put this into units of nanoseconds. And so the period is 5.18 times 10 to the minus 15th seconds. And I'm going to put seconds, a 1 second in the denominator to cancel seconds. And I'm going to say 1 second is 10 to the 9th, or 1e 9th nanoseconds. And 15 minus 9, or 9 plus negative 15 is negative 6. So I get 5.18 times 10 to the minus 6th nanoseconds. Wow. 193 terahertz is a high frequency. And this is typical of the light wave in a fiber whose period is just unbelievably small. It's even a millionth of a nanosecond. Okay. Let's go ahead and calculate the wavelength now. And what we're going to use is the equation for the wavelength and the speed. The speed is distance divided by time. And the distance it goes in one period is called the wavelength. And so it goes a distance of the wavelength in a period. And so we have V equals lambda over T. So here's the equation, and we have V is equal to 2 times 10 to the 8th meters per second. And now I'm going to go ahead and solve the equation for the wavelength. We want to calculate the wavelength. So lambda is velocity times time. And we're going to go 2 times 10 to the 8th times t, which is 5.18 times 10 to the minus 15th. And let's go ahead and calculate these numbers. Times 2 times 10 to the 8th equals, and I get 1.03 times 10 to the minus 6th. And they say we want the answer in units of meters. Oh, so this is what we get. 1.03 times 10 to the minus 6th meters. Okay. Let's express the wavelength in nanometers. Lambda is 1.03 times 10 to the minus 6th meters. And I'm going to put 1 meter in the denominator and say 1 times 10 to the 9th nanometers is 1 meter. And if I multiply 10 to the 9th times 10 to the minus 6th, I get 10 to the plus 3, and I get 1.03 times 10 to the 3rd meters. This isn't right. 2 times 10 to the 8th, 5 times 10 to the minus 15th. let's double check this. 5.18 times 10 to the minus 6 nanoseconds. Lambda, 10 to the minus 6 meters. This is, yeah, it's 1,000 nanometers. Nanometers, John. Okay, so we get 1030 nanometers. That's that all-important sanity check part of the equation. Okay, 1,030 nanometers. Let's put it into micrometers. Lambda is 1.03 times 10 to the minus 6 meters times 1 meter is how many micrometers? 10 to the 6th micrometers. And this gives us, hey, the 10 to the minus 6 and the 10 to the plus 6 just cancel out, and I get 1.03 micrometers. Okay? And that's right. 1 micrometer is 1,000 nanometers, and 10 to the minus 6 meters is a micrometer, and so it's 1 micrometer, and this all works out. Okay, so this is a 1 micron wavelength light wave in the optical fiber. Hope this helps for this problem. Thanks for listening.